Now that you've had an overview of DSE Graph, we're going to take a look at managing property graphs. We'll do this using two main sections of content. The first explains property graph data models, and the second explains operations on the graph property data model itself. Let's start with an overview of the graph property data model. Mathematically, we can define a property graph as a directed, binary, attributed multigraph. It consists of a set of vertices, a multi-set of directed binary edges, and key value pairs of properties associated with vertices and edges. For those that don't come from a mathematical background, property graph data models represent graphs using three elements: vertices, things, edges, relationships, and properties, attributes on either vertices or edges. Each vertex in a property graph has a unique ID that is specified by a graph creator. The name of the ID type for DSE Graph is a user-defined vertex ID. Each vertex also has a label that generally denotes a type of an entity that a vertex represents. In this illustration, we have 7 vertices with labels: movie, person, user, and genre. All of these vertices have unique IDs, such as M267 or P4361. It is convenient for us to think of IDs as simple strings in this example, but in reality, vertex IDs in DSE Graph are frequently composed of multiple components, used not only for uniqueness, but also for graph partitioning. We'll talk more in a subsequent section of this course about how to use IDs to achieve data locality in DSE Graph. Each binary edge connects exactly 2 vertices. Edges are always directed, have automatically assigned unique identifiers, and have labels. Since a property graph is a multigraph, it is possible to have multiple edges connecting the same 2 vertices. Such parallel edges may have the same direction and labels, but will have different IDs. In this illustration, we connected our vertices with labeled edges. Edges and their labels usually denote relationships between entities represented by vertices. It's getting more interesting. We can now read that some user U185 rated movie M267 that has some actor P4361. Though edges are created with direction, DSE Graph automatically stores both directions in and out of an edge to ensure users have the flexibility of traversing an edge in any direction with the same performance. Properties are key value pairs that can be associated with any vertex or edge in a property graph. They describe individual vertices, the entities, and edges, those relationships. Our sample graph now contains a lot of useful information. Take a look, we can see properties on both the vertices and edges. A vertex property that can have multiple values is called a multi-property. In this example, we have production and budget as multi-properties and show their values in square brackets. Another way to think about them is having multiple key value pairs with the same key. For example, budget. Budget could have $150 million and $200 million. Note that multiple properties are only applicable to vertices and not to edges. A property that can be assigned to a vertex property is called a meta property. Meta properties are usually used for describing access control, provenance, and audit information for individual vertex properties. In this example, we have meta properties describing provenance of 2 movie budget estimates, as well as meta properties describing access control for permissions for the person properties. Note that meta properties are only applicable to vertex properties and not to edge properties. A meta property cannot be a multi-property or have meta properties assigned to it. Here we see all of these concepts combined to create a robust data model that represents a real-world graph. We can see persons and movies and how they relate, whether actors or other actors. We can see users rating movies. We can see movies belonging to genres. We can also see a lot of great information about the movies, whether we're talking about the budget multi-properties or the budget meta-properties from Bloomberg Businessweek or the Los Angeles Times. Graph databases are based on graph mathematics. Though not required, it is helpful to know the meaning of a few graph theory terms. So let's take a look, and we'll use the example on the slide to explain some of these terms. First, let's start with incident edge. An edge is called incident to a vertex when the vertex is one of the edge's endpoints. For example, actor is incident to movie M267, or rated as well as another incident edge. Incoming and outgoing edges. An edge is directed either in or out of a vertex. So for movie M267, we see an outgoing edge actor to P4361. We see an incoming edge rated from the user vertex in this example. Vertex degrees represent the number of incident edges belonging to a vertex. We can have in degree or out degree, and actually vertex degree represents the sum of in degrees and out degrees. So for this example, the vertex movie M267 has a vertex degree of 4, with 3 outgoing degrees and 1 incoming degree. Adjacent vertex. A vertex A is called adjacent to a vertex V when there exists an edge between the two vertices. For instance, we see that movie M267 is adjacent to person P4361. Path. Path is a sequence of alternating vertices and edges, beginning and ending with vertices, where each edge's endpoints are the preceding and following vertices in the sequence. Here we see a path from user through rated to movie M267 and out through the actor edge to person P4361. There are special types of paths in graph theory. There's a simple path, which is a path that cannot repeat an edge or vertex. There's also cyclic paths. A cyclic path is a path with repetition and therefore cycles. There's also the shortest length path. This represents a path with the least number of edges to get from one vertex point to the other. Finally, subgraphs. A subgraph S of a graph G is a graph whose vertices are a subset of the vertex set of G, and whose edges are a subset of the edge set of G. So here we have a subgraph of movie and person out of our full graph. To summarize, this illustration shows a subgraph of the original graph we saw previously, with 5 vertices and 4 edges. Vertex M267 has 4 incident edges, 1 incoming and 3 outgoing, and 4 adjacent vertices. Only simple paths exist in this subgraph. This is only to get us started. There will be plenty of new notions introduced gradually throughout this course.